Let's see. I will begin with a word of prayer. Let us begin. Dear Heavenly Father, we thank you for this day. I thank you for the students. Just ask you to bless this time, Lord. In your name I pray. Amen. So yes, I have, I'd say I'd send a link, but we found this Googling on Mrs. Guthrie's computer. So I guess I can scan it and send a link to the class or something. I don't know. I'm not sure if am I allowed to scan this and send it? Yeah, they got their website on there. I don't feel bad about posting a PDF of this. This is from Printable 3D Shapes Tetrahedron-net-tabs.gif https www.mathsalamanders.com/image files printable 3D shapes. Whatever. Anyway, if you Google it, it came up pretty hard. I looked for tetrahedron cutout sheet, and I found this. And so the reason I made this, well, one of you made this. Thank you for that. Is to think about problem 47, right? So we can think about the faces. Maybe I should do this closer to the camera, actually.
But then we can't.
Yeah, if you forget those people. That's right. So let's see here. Are you going to be sad if I color one of these faces? Okay.
That one is yours. You can do whatever you want with it.
Is that right? Oh man, left my markers back. I guess I'm going to have to use colored pencil. Woo! Ow! I'm going to get stuck down here. All right. This is not going to show up great, but it'll have to do. Sure you got a red marker? That's okay. So if we think about one of these faces on the tetrahedron, what I need to do, all right, so if we think about the set of faces on the tetrahedron, right, let's think about that. Our set is, so here's my tetrahedron, badly drawn. So we've got face 1, face 2, on the back side, face 3, on the bottom, face 4. All right? And so the set of faces, F1, F2, F3, and F4, of course, we can look at the set of faces is the point. And if you look at the symmetries of the tetrahedron, right, then if you think about it, if you start with one face, well, first of all, if you think about the symmetry of the tetrahedron, what is the symmetry of the tetrahedron? What do we define that to be? Do you remember? So the symmetries of the tetrahedron are what? We need. It's a subgroup of the isometry groups, a group on R2, such that what? Such that sigma, so sigma is in here, if sigma of t is equal to t again, right? So if you think about that, it naturally descends to mapping faces to faces. So any permutation is actually going to map a face to a face. So you can think of it instead of as a mapping on the set of all points that form the tetrahedron, you can equally well think about the symmetries as mappings on the faces themselves. All right? And so that defines a group action, and so we can use the orbit stabilizer theorem as the symmetry group acts on the set of faces, right? And so, like, what's the orbit of one face? Can you tell me what the orbit of face 1 would be? So if we think about, I use the red one to be face 1. So we could do what? We could rotate the thing down like that. So then it's reached the bottom face. We could start with that face and rotate, around the top like that, or rotate around the top like that. So as you can see, the red face can be rotated or one way or the other, rotated or reflected. I guess just rotated. I don't know. Anyway, by various symmetries of the tetrahedron, we can move the red face to any one of the other faces on the tetrahedron, which is to say that the orbit of face 1 is what? It's actually S again, right? It's the whole set of face. This action is transitive. Face 1 orbits to all the other faces. So what's the, we have that the size of the orbit of face 1 is equal to 4. Then the question is, what's the stabilizer of face 1, right? So as you think about the tetrahedron, what isometries are there of the tetrahedron which fix face 1? What could I do? Yeah, I can like rotate it like that, right? I can rotate it like that. So I've got rotations. Flip it around 3 times. The identity, yeah. And then there's the ones that I can't illustrate with this toy model. Like I could fix the top point, but exchange these two. Now I'd actually have to tear my model to do that, right? But technically speaking, that's still a symmetry of the tetrahedron. It's an isometry. It's just not a physically possible motion. So if you start thinking about that, you've got reflections around basically any of the bisecting axes of the face. If you really just stop and take a look at what you're saying, you're looking at nothing more than D3 again. So we have a copy of D3. This is up to isomorphism. It's isomorphic to D3 because you've got the 3 rotations and the 3 reflections. So then orbit stabilizer says what? That the symmetry group, the size of the group is the product of the size of the stabilizer with the size of the orbit, which is apparently 6 times 4, so 24. That's the analysis for faces. And you can go through, and in fact, the action is transitive on the set of faces, on the set of edges, and on the set of vertices. The challenge in each case is to see what of the isometries of the pyramid actually fix the set. So I'll let you guys play with that for a couple minutes. I want to get something from my office and do a similar thing for a cube. It'll just take me a minute to go run and get it. It's better, isn't it? Yeah, it's better. Emily knows. I'll leave that mic there to sweep on you. Uh-oh. I have locked my door. If I had a tetrahedral jar, that would make it.
I don't understand how you can have a tetrahedral jar. Like, how are you? Where's the top to put stuff in it? Would you just take one of the faces off? Is that still? But then the stuff would fall out.
No. It would just, the cap would be like right here.
Yeah, but what he wants is you to pull the face off, as you'll see when he brings his jar back.
I feel like what if you just had like a little frame that was like the edges, and then you could have like a face that could pop?
You'd have to have
But
a
the
stand
stuff's gonna
for
fall
it.
out the side.
You'd have to have a stand
well,
for it.
like
You have a
this.
stand and you put the
You
stand
just
over
hold
it.
it like
Yes,
this,
we had a
and
stand
then like a
for
little
it, it
ice
would
cream
work.
cone.
Yeah, that could work.
See you looking for something of infinitely more value. Crappy. Look at this side. I don't even know what happened here. Just trying to tape it from the inside so it wouldn't look like garbage, but
Yeah, I
Symmetries.
But because it's the orbit stabilizer theorem, you get like 24 for all of them.
Wait, so did you just give us the answer?
Yes, that is the answer to part A, right there. Yes.
Sorry, I'm being very low.
Wow.
Can you hear me?
I didn't
The
understand.
internet.
So why? So
Have you noticed though it doesn't really pick up people's voices? No. So unless you go over there and like shout in the microphone. No, it's right there. He left it. So it can hear. Yeah, that's what he said. I'm waiting for you to sneak on you. Oh, he said that? Yeah.
Yeah, we are kind of close to that. Like,
That's
all we're
true.
thinking is
Well, I got
like,
well internet. The answer number 4 is that. Yep.
Wow.
Congrats to anyone who watches the videos. Welcome to Swan.
I will begin with a word of prayer. Thank you very much. I think all of our ideas are wrong, deeply wrong.
You want another quote? Yeah, we all need to live in delusions. I'm approximately as I have.
But, you know, we all need to live in delusion sometimes.
It would be nice if we could get more people to learn. Quaternions are nefarious, is another quote.
Quaternions are quite nefarious, but it would be nice if we could get more people to learn.
You changed.
Wow.
Check the video, I'll find out. Post the what?
The whole video on YouTube.
The whole. I don't think it stopped, so it should still be there.
Yeah, exactly.
Huh. Wonder what I'm gonna. Huh.
It was nothing that has not already been.
So I like this as a model of the cube because you can easily see that there's 1, 2, 3, 4, 5, 6 faces. And then if you want to think about one face, you can think about, is the orbit of that face transitive? Can you orbit that with a, well, I mean, of course, you can rotate like this, or like this, like that, right? Get all those. And you can also go this way and this way. So clearly this face orbits to all other positions, all other faces on the cube. And then you can start asking the question, well, what's the stabilizer of this face, right? So I'll look at it this way for you guys. So of course we can start like this, and we can rotate, 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 and then get back to where we started. We've got the 4 rotations, and that's all that's physically possible without tearing the cube apart, right? But we also have these kinds of rotation, these kinds of symmetries. See, I can't do that without ripping the cube apart, but that's also a symmetry. The face is still fixed. Or I can flip it this way. That's a symmetry, right? Or I can flip it end over end like this, right? Or I can flip it end over end like that. And that's why the stabilizer of a face with respect to the symmetries of a cube is really D4. It's the two-faced transformations of a square. So that's a demo. I should have had this in class. I shouldn't have brought my kids that day so we could have done a better job. But that illustrates why there are 48, because 1, 2, 3, 4, 5, 6 faces times D4, which is 8 things, so 48 symmetries of a cube. However, 24 of those are not motions, because they're not motions in the sense that they're disorienting. A motion it maps a right-handed triple to a right-handed triple. It maintains the orientation of edge vectors, but this is not a motion. It actually disorients the cube. It's turned to face inside out. And actually, when you do that, I think when I do that, other things happen to the other faces as well, which I can't illustrate with a glass, but anyway. So I thought that was useful. But you see why I need the tetrahedral jar. Or other shapes, right? I don't know. Okay, you guys have other questions? Maybe? I still haven't fixed that typo. That's PAP inverse. What's that? 43 looks hard. 43 is harmless. I think 48's hard. Not really that it's hard, it's just tedious, right? Now the smart thing to do.
Number 50 looks really hard.
Eh,
When will we have 49?
when will you have 49 and 50? That's a good question. That depends on when I write them tonight. Let's see here. One thing we should do is to search for alternating group. Here's the A3. Oh, look at that. Ta-da, there's A4. So, I mean, it's good if you didn't know how to find them already, that you went through the thought process of doing it, but here's a check. Right now you just got to decide what are the conjugacy classes in there, right? So you already know that two permutations are conjugate only if they're have the same cycle type, right? But that conjugation may or may not be possible with an element of A4. So to actually figure out which ones are conjugate to which ones and what the exact things are, I'd have to do a bunch of computation, but it's straightforward, just tedious what to do there. So, yeah. So what I'm trying to say is you'd actually need to, like, you know, start doing some calculations. 2, 3, 4, that's here, right? Try conjugating that by, I don't know, it seems like 1, 2 ought to do something to it. Oh, but I can't do that. Why can't I conjugate by 1, 2? Oh, wait a minute, or can I? No, I can't. Our universe is A4, right? So I'm not allowed to conjugate by an S4 thing. So I got to conjugate by, I don't know, I guess I could do 1, 2, 3, 4, see what that looks like. What's the inverse of that? I think it's its own inverse, isn't it? Yeah.
So is it GX G inverse or G inverse X G?
Well, it doesn't matter, because this is equal to how can I say this? I mean, words.
Well, if that's equal to X,
So like, there's not going to be any difference in terms of what are possible conjugations.
but for the group action, it does matter.
Yeah, it does. That is true. For the problem that I had a typo in, it matters. Yeah. That's a different thing, though. Because they're, well, it's a different, bah. Words. Or was that mission, what are we on? Huh. This one. So, yeah, that's not within a group, right? We're acting on n by n matrices. So it's, I mean, it's a slightly different animal. I mean, it does look much the same, but, and I guess I should say, although admittedly, I could trade out P for P inverse and I would have the opposite thing. But the trouble there is it's also got to be P times A, and that's where we get into trouble with the P times A not being consistent with the axiom of the you know, if with my current wrong definition, it's actually true that P times, well, let's say PQ times A actually works out to, I think, Q times P times A. Is that right, Emily? Isn't that what we found? Yeah, so it's actually not, that's not axiom 2, right? But if you put the inverse on the other side, then things work out, like the axiom works out nicely. You get PQA, which is what you need, assuming, of course, P times A is PA, P inverse. I think you knew this. You were asking me about this like earlier this week. I guess what I'm trying to say is it's not quite the same as conjugation, because conjugation's within a group, yeah. I'm not sure what I can add to your question. I see what you're saying, what you're getting at, but okay. So here is a specific conjugation of the 2, 3, 4 cycle. Now we believe, if we trust the theorem, that now you guys made me. We believe it should conjugate to one of this guy, or 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 this guy. One of them's my choices, right? It has to go to a 3 cycle. Which one does it? Did you guys work it out?
I got 1, 4, 3.
1, 4, 3. Yes, right. I believe that's right. So what does this tell us? This tells us that the orbit under the conjugacy action of, 2, 3, 4, right? It's equal to, well, we already know 2, 3, 4 is in there from general theorems, right? Like any element is in its orbit. The orbit of an element includes the element itself by the action by the identity element. But you know what? We also got 1, 4, 3. And orbits are that orbits disjoint partition the set, right? In this case, the set in which we're acting is A4. So we know those 2, 3 cycles belong in that conjugacy class. So what do you got to do? May I suggest you take 1, 4, 3 and conjugate it by something? See where it goes. Right? If it goes back to one of the 2 things you already have, try something else until you're sure that that orbit has just those things in it. Eventually, you're going to run out of things to conjugate to. And you'll see that certain things are related to other things and some are not. And you just continue this calculation. Like instead of doing 1, we could try what? Like 1, 1, 3, 2, 4? See what happens to that? What would that get us? I'll start out. 1. Two, yeah. Looks like we got a 4. Hey, now we know this orbit has at least 3 things in it, right? Can you tell me anything about the size of the orbit? What did we learn? The size of the orbit divides the order of the group. I think that's true. So what does it have to be? What are your choices? Yeah, 3, 4, 2, or 6. But it can't, well, Yeah, 3, 4, 2, or 6. We got. What else do we know, though? There's something else we know. What was it? What would the class equation say? Is that relevant here? Ah! Let's see. In S4, I found there were 5 distinct cycle types. 1, two cycles, 3 cycles, 4 cycles, products of 2 cycles. 1, 6, 8, 6, and 3. Those are all divisors of 24, right? And the sum of those numbers is also 24, right? So the other thing we know is we know each orbit must divide, the size of each orbit must divide 12, but we also know that the sum of the orbits must also divide 12, right? Equal 12, sorry. So, I mean, you could have something like 2 plus 2 plus 2 plus 2 plus 2 plus 2 equals 12. You could have 6 plus 6 equals to 12, right? You could have 3 plus 4 plus 3 plus 2 equals to 12. I mean, you got all kinds of, although there's got to be a 1 in here, doesn't there? Because one of the orbits is the orbit of the identity permutation. So this is not the case. That's not the case. Got to be looking for an answer which has, the size of the orbit of the identity permutation is just 1. So you are looking at 1 plus a couple of numbers maybe, which is equal to 12, and those have to be divisors of 12 as well. You can kind of anticipate some things if you think hard enough about this, but honestly, you can just calculate the conjugation just the same. It's probably faster. But you can check your answer with this, right? I also would say that the cycle type, like it's only conjugate to same cycle type, right? So if we look at the list of A4, how many 3 cycles did we have? We have 6 of them. How many? 8? There were 8. Huh. So I wonder how far that's going to go. I bet they're not all going to be conjugate. If I had to guess, I'm guessing that 8 is going to split. Oh yeah, there you go. Perfect. 8 does not divide 12. It has to split. It has to split to what? 4 and 4. Seems like it could split to a 2 and a 6, but that seems unlikely unless that one goes to 6. I mean, I don't know. If you find one of the orbits has just 2 things in it, though, then you know that the other one's got 6 in it. If you're so fortunate as to calculate the one with 2 things in it, you save yourself the calculation with the other 6 things. I mean, these are kinds of labor-saving. But yeah, if I had to guess, I'm going to say we're going to find that the 3 cycles split into 2 classes, and then, I don't know. I shouldn't speculate more without doing calculation. I think I've done enough that you guys know where to. Okay. Let's go back and look at the problem you thought was hard. I think that one's easier. So I said here, you got normal subgroups, H and K, right? You're supposed to prove that K mod H is a normal subgroup of G mod H. So what's your question? Is there a particular question in here, or?
I think I'm just a little bit
Okay, so fair question, I guess. So let's just, first order of business, talk about A. What do we have to show there? We're supposedly going to show that K mod H is a normal subgroup of G mod H. Right, and what else do we know? We know that H is a subgroup of K. That's given, right? What else do we know? Oh, H and K are normal in G, right? So we know this, and we also know that H is a normal subgroup of G. We know that K is a normal subgroup of G. These things are given. So to show that K mod H is a normal subgroup of G mod H, we need a few different things, right? We need that K mod H is a subgroup of G mod H, right? And we also need that, G, K mod H, G inverse is a subset of G mod H, right? And this would be for any G in G mod H. But let's unpack that. What does that really mean? What is it? What does a G in G mod H look like? It's a A times G equals to, you said A times H for some A in G. Is that right? Yeah. And so what's G inverse in that context? As we've discussed, it's A inverse times H, right? The inverse is represented by the inverse, the representative. So this condition amounts to, I need to check that A, H, when it conjugates K by H, I need to check that that is a subset of G by H, yeah. So if I just do direct battle on this, if I don't have some kind of, clever insight into how I should do this, I will not be clever. I will resist the urge of trying to be clever, and instead just do direct battle, as you guys would likely do. So what we do is we pick a point in here, and we want to show it's in there. So pick a point. Let's let x be an element of that. What would that mean? Then x is equal to what? It's equal to AH times what? Times, let's say, K times H, right? Times A inverse times H. I still have not proved, by the way, that K mod H is a subgroup of G mod H. I'll leave that to you guys. I think that's easier than what we're doing. I could be wrong. Anyway, so this times that for what? For some K where? In the big K. Okay. Sorry, I'm an idiot. And then so that's A, K, A inverse, inverse of times H, right? right? Which is an element of G mod H, since A, K, A inverse is an element of G. That seems too easy. Right? I'm not saying it's wrong, I'm just saying this wasn't that bad, was it? Hmm. What does that show, right? I think, yeah, I think at this point we've shown that we've shown that G, K mod H, G inverse is a subset of G mod H for arbitrary G. Right. So this implies that AH, K mod H, A mod H inverse is a subset of K mod H, right, for all AH in G mod H. Therefore, K mod H is a normal subgroup of G mod H, right? Because that's the definition of normal subgroup, is that when we conjugate, it's a subgroup of the normal. Oh, wait a minute. Oh, I think I'm remembering. Yes, tell me, Liam. Why am I wrong?
Well, is it an issue with your...
What's in brown?
No, we're not talking about what's in brown. Well, I'm talking about just the fact that you
Oh,
said
it's also in
G.
black.
Okay, yeah. It should be K.
Yeah, that's why it's too easy. It's because it's wrong. Because what I just wrote down is impossible not to be true. Sad. Sad. Good grief. K. That's a K. This is a K. Otherwise, there's no condition to be had there. Duh. Gee, George. All right, so, yeah, let's try that again. All right. There we go. Thank you. Sometimes when something seems too good to be true, it's just too good to be true. All right. Okay, so what do we need to show? We need something a little bit pickier. We need what? We need a K inverse to be an element of what? We need it to be in K in order for this to work out for us, right? But notice that A, K, A inverse is a subset of K by K normal subgroup of G, right? So therefore, a K inverse is already in K because K is normal, which means that when you conjugate elements in K by group multiplication, you're again in the subgroup. Normal subgroups are closed under conjugation by the supergroup in which they live. So this is an element of, this is in K. So therefore, X is an element of K mod H, and so we have normality of K mod H in G mod H. I don't know. Isn't there a map? Can you define a map F from K to G? Say f of x equals to X. Is that a homomorphism? I think that's a homomorphism. Yeah, it's not. It's kind of the. It's not exactly the identity, right? Because the domain and the codomain don't match. But what if we looked at another map, like I don't know, f bar of I don't know kh equal to I don't know kh. Now that's definitely an element in G mod H, yeah? Is that a homomorphism? I think F bar. I think F bar is a homomorphism from, K mod H to G mod H, yeah? Is K a super? Yeah, K is a supergroup of H. Does that make sense? I think it's a homomorphism. And it's fine. I try to be lazy and figure out some kind of proof that this is a subgroup of that without actually doing any work, but I think it's making more work, so I'm going to stop. But I can't help thinking there's some kind of stupid map argument that will make our life easier. But you can just prove that that's a subgroup of that directly, right? You just proved it?
No.
Okay, are you going to just...
Repeating you.
No, we'll just prove it.
He's repeating me? Isaac will do that. Like I go home for dinner and I say whatever, and then he's like, whatever, and I'm like. So then what I've gotten in the habit of doing is I'll start saying, well, the third tensor category of the abelian subalgebra of the matrix subgroup of the the tensor is the transpose of the third power of the sine function. It means nothing, right? But then Isaac will be like, blah, 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 blah. I'm like, oh, man, he's already got a solution. He's put on the student filter. So let's see here. But, yeah, we have kids like that, yes. Okay, so do you guys want to talk about the well-defined? So that psi, so you guys can prove the subgroup, right? I don't think that's, you'll get that part. All right, so allegedly psi is a mapping from where to where? G mod H to G mod K. Right, and what else do we know? The mapping is given by GH equals to GK. So I say in part B, what do I say? It show psi is well-defined. Right? So when I think about well-defined, some people insist on well-defined just meaning that the map is single-valued. When I use the term well-defined, I'm talking about the totality of what's going on. For me, well-defined includes the domain being reasonable, the codomain being reasonable, and also the fact that the function actually is as advertised, a function that it's single-valued. So here, there's really nothing to check in terms of domain and codomain, right? You look at the formula. We've given a formula which covers every possibility for the domain, right? And the output, GK, is clearly something in the codomain. So there's no question of into here, as I said the other day. Right? Into is obvious. It's definitely into G mod K. The question is just about single-valued, right? So check it out. We know that G1H equals to G2H if and only if what? learned? G1 inverse, right? G1 inverse is an element of, G1 inverse times G2 is an element of what? H, yes, yeah, right, H. But what is H? It is a subgroup of K, right? So that means that G1K equals to G2K if and only if G1 inverse G2 is, I mean, this is just, okay, I mean, both 1 and 2, I'm just referencing an earlier lecture. Set aside this comment right here for a second, right? So think about it. If we have psi of G1H equal to psi of, well, let me say it this way. Psi of G1H is equal to G1K, right? But that's equal to G2K if we're assuming this, all right? And that's equal to what? However you want to package this, it's clear it's single valued because the output when we look at representative G1 is G1K. The output when we look at representative G2 is G2K, but G1K and G2K are the same coset in G mod K. So that means it's single valued. Yeah.
So is it just saying if you put in equal output, if you have equal inputs, then you get equal output?
Right. The issue is equality is masked by the ambiguity of representatives for the coset space. So that's single value. The fact that the kernel is K mod H is not hard to come to. Do you guys have any ideas about part C?
Wait, the first part was already done in part A, right?
Right. That's true. But you can get it again from part B. So here's the hint I would have for you. You should think about the mapping psi, right? What did I say? I said that psi is a homomorphism. Its kernel is K mod H, right? So the kernel of psi is a normal what? Right, normal subgroup. Kernel of psi is a normal subgroup of its domain, which is G mod H. So since the kernel of psi is actually equal to K mod H, that gives you an alternative proof that K mod H is a normal subgroup of G mod H. So if you did part B and C first, you wouldn't have to do part A. Wait a minute, maybe that gives us a workaround to the proof it's a subgroup, huh? Because it actually, the kernel is a subgroup. We had that the kernel was a subgroup before we had it was a normal subgroup, didn't we? Yeah, we did. And, you know, we'd have everything we need if what the first isomorphism theorem says. It says that what does it say? It says the domain, which in this case is G mod H, right? Mod the kernel, which allegedly is, what is it? What was the kernel? I keep forgetting. K mod H. And allegedly that's, well, the first isomorphism theorem says that's isomorphic to the image, right? The range. So if the range of G mod H is actually G mod K, I guess we're in business. Oh, I'm sorry. In other words, but I messed it up. I mean, in other words, what I'm trying to say is we need this is equal to G by K, right? In other words, if you can prove that psi is if you can prove that psi is onto then you get part C from the first isomorphism theorem, is what I'm trying to tell you. So I would encourage you to attack it from that perspective. Try to prove that psi is got kernel, k mod h, and that it's an onto map. If you got that, you get part C, and you also get the rest of part A that we haven't done yet. I do think it's instructive for us to go through part A as we did. That's why I did it. But I also know that there's a duplication there that's not intentional. Other questions? I showed some of you how to do 44 and 45. Have you shared that with the others? Oh, okay. So the basic idea is this. When we're looking at the matrix, a matrix group acting on Rn, it's often helpful to just focus on something really simple to rotate. So like E1 is pretty easy to work on. And if I take A times E1, right, that would give me column 1 of A. So if you just think about that, if you think about the orbit of E1 under arbitrary invertible matrices A, you should be able to kind of convince yourself intuitively that the orbit is everything non-zero. Because you can make column 1 of A whatever you want, right? But I have a better way, a more geometric way of looking at this, and here's how it goes. Suppose we want to orbit over here to the point A comma B, right? Then, of course, you can look at the unit circle like that, right? And you can rotate E1 over to here by a standard angle theta. And that would give us this point over here, let's say R theta E1. Now R theta is cosine theta minus sine theta, cosine theta. That's the rotation by angle theta. That moves E1 over to R theta E1. That's definitely an invertible matrix, by the way. And then what I do is I move this point R theta E1 out to here by a dilation. So I move that out to here. I say, aha, well, I'm going to do the square root of A squared plus B squared times this R theta E1. So my claim is that if we set A equal to the square root of A squared plus B squared times the rotation by the angle theta, where theta is the standard angle of A comma B as a point, then that matrix is invertible, right? That's an invertible matrix as long as A and B are non-zero, as long as A comma B is not the origin. Do you agree? This is an element of GL2. And indeed, the determinant of A is actually equal to the square root of A squared plus B squared if you work it out. But I would point out that shows you that the orbit of E, right? The orbit of E1 includes what? It includes A comma B for A comma B not equal to, 0, 0. But A and B are arbitrary. So in other words, the orbit of a non-origin point for the GL2 is just the punctured plane. It's everything except for the origin. That's the solution to 44, except you still got to think about the origin. Why am I doing your homework for you? Hey, we were supposed to talk about problems from the book. What happened? It's my fault, isn't it? I didn't bring the book. You should give me a poke about this, because otherwise I'll just solve your homework for you, and that's no fun. I'm never going to get poked, am I? So if you think about 45, it's much the same, except in 45 we're just looking at multiplication by O2 matrices, right? And there, I can't do the dilation, right? O2 matrices maintain the distance from the origin. They're orthogonal matrices. They maintain distance. So like the orbit of an O2 matrix falls on a circle, if you think about it. Work it out. So there's lots more orbits for problem 45 versus 44. And for 46, it's more interesting still because the orbit there, you're thinking about orbit by similarity transformation, right? To describe the orbits nicely, you'd like to explain when are two matrices similar. Now, I gave you an answer to that question in linear algebra, but maybe you've forgotten about it. So with that, we'll stop.